In the previous lecture, a simple model of a sound wave was studied through the fluctuations of air density in terms of time and space. Here is an example of a graph of the air density variations from the mean along a line going away from the source, which was located to the left. The wave was traveling from left to right. Nothing was said about the role of the amplitude, which was defined as half the difference between the maximum value and the minimum value of the physical quantity describing the wave. Quantities that could describe a sound wave are the air density variations from the mean, the component of the displacement of air molecules from their equilibrium position, the x component of velocity of the air molecules, and pressure variations from the mean pressure. I added this last one because it is a typical quantity to describe sound waves, even though I have not explained what pressure is yet. Graphs of these quantities would have all the same wavelength and period, but would have different amplitudes with different measurement units, which none of them are joules. However, if one of these quantities increased its amplitude, all the other amplitudes would also increase. The more energy the wave transports away from the source, the higher are these amplitudes. When it comes to sound, the higher these amplitudes, the louder the sound. When it comes to sound waves, we are interested in knowing the rate at which the energy is transmitted to the listener or to the microphone. Let us abandon the model of the sound wave that travels only in one direction and look at a source that sends energy in all directions at once. The surface of constant phase would be a sphere. Let us say that we only draw the surface corresponding to the maxima of air density variations from the mean. There is a new one of these that appears every period. The smallest distance between similar phase of the wave is still the wavelength. Each part of the wave is traveling away from the source. On the slide, it looks two-dimensional, but the shape of the medium for each wavelength is a spherical shell of one wavelength in thickness. Let us say that the work done by the source on the air nearby during one period is delta ES. The power of the source is then delta ES divided by the period. For simplicity, we will ignore the loss of energy due to friction and heat and assume that all the energy travels through the medium without loss, a rather unrealistic assumption. The energy of one wavelength of the medium is transmitted to the next spherical shell of the medium in one period. Essentially, the energy is traveling at the speed of propagation of the wave. By conservation of energy, each cell receives delta ES amount of energy from the spherical shell behind it and transmit delta ES of energy to the spherical shell in front of it. Notice, however, that the volume of the spherical shell is increasing as the wave travels away from the source. A larger volume means a larger number of molecules to which the energy is transmitted to, which means that on average, each molecule farther away from the source is getting less energy through the passage of the wave, which means that the amplitudes of the x component of the velocity and the displacement from the equilibrium position are getting smaller as the wave is getting farther and farther away from the source. Let us now look at the power that is transmitted to a listener or to a microphone. Unless the listening device can put itself in the path of the entire spherical wave, it will only catch a portion of the energy of the wave. Here is our source of sound waves and a wavefront reaching a listening device. Let us use the variable r for the distance between the source and the listening device. It is also the radius of the spherical wavefront. For the listening device to be able to capture energy from the sound wave, it must come into contact with the wiggling air molecules. The more contact with the air molecules, the more energy is received by the listening device. Let us assume that the listening device puts out an area A in the path of the incoming wave. The maximum power input from the wave to the listening device will be a fraction of the power from the source. Let us say that PL is the maximum power received by the listening device. We can write the maximum power transmitted to the listening device this way, where the factor in bracket is the fraction of the area of the whole spherical wavefront that is captured by the listening device. 4 pi r squared is the area of a spherical wavefront of radius r. Let us regroup the quantities differently. The quantity in the bracket is the power carried by the sound wave per unit area and is called the sound intensity. The variable name capital I will be used for sound intensity. The measurement unit is in watt per meter square. Capital A is just a characteristic of the listening device. The human ear can only hear sound waves with frequencies between 20 Hz and 20 kHz. Outside that range, sound waves are possible, but we cannot hear them. Even in the audible range, the sound waves must be powerful enough for us to be able to hear them. A sound intensity of 10 to the minus 12 watt per meter square, which is the same as a picowatt per meter square, is barely audible and is considered the threshold of hearing. On top of that, the threshold of hearing varies with frequency. Low and very high frequencies in the audible range require higher sound intensity than 1 picowatt per meter squares to be audible. The range of the sound intensity is wide, and a sound intensity of 10 watt per meter square is considered to be the threshold of pain, and such a sound is damaging to the ear. Because of this wide range of values, another quantity is more often used to characterize the loudness of a sound. It has to do with the exponent that you have to give to 10 to get the ratio of the sound intensity and the sound intensity at the threshold of hearing. That exponent is called the sound intensity level, labeled with its acronym, and is measured in Bell in honor of the inventor of the telephone, Alexander Graham Bell. For example, the SIL for a sound intensity at the threshold of hearing is equal to 0 Bell. Similarly, the SIL at the threshold of pain can be evaluated to be 13 bells. However, the most well-known measurement unit for the sound intensity level is the decibel, for which there is 10 decibels in 1 bell. Just like there is 10 deciliter in 1 liter. The sound intensity level at the threshold of pain is then 130 decibels. Let us now do an example using these concepts. You are listening to a speaker and measure the sound intensity level at your location to be 74 decibels. If the power output of the speaker is doubled, what would be the sound intensity level at your location? One given is the initial sound intensity level, which I have expressed in Bell because it is with that unit that the sound intensity level is defined in the equation. The other given is about the doubling of the power output of the speaker that we can formulate this way. Using the definition of sound intensity, initial and final, we can write the previous equation this way. Since we did not move in respect to the speaker, the distance r did not change, and the expression can be simplified. Now let us use the definition of the sound intensity level and simplify the equation by removing the common factor of the sound intensity at the threshold of hearing. At this stage, you could substitute the value of the initial SIL, and by trial and error, and with a scientific calculator, you can get an estimate of the final sound intensity level. But because I have already defined the log base 10 function in the lecture on half-life, I will use this concept again. I will write the number 2 as a power of 10. By definition of the log base 10 of 2, log 2 equals the exponent you have to give to 10 to obtain 2. Next, I use the law of exponents, where the product of power of the same base equals that base to the power of the sum of the exponents. Now, equating the exponent on the left-hand side to the exponent on the right-hand side of the equation gives this. Using a scientific calculator to evaluate the log base 10 of 2 and substituting the initial sound intensity level in Bell gives this. The final answer is 7.7 Bell, which is the same as 77 decibels. Notice that the doubling of the power output of the speaker results in an increase of 3 decibels for any listener, no matter where they are in respect to the source, under the assumption that there is no energy loss through the medium. Our study of waves so far has been restricted to longitudinal waves, for which sound waves traveling through the air are a prime example. But there are other types of waves in nature, and they will be the subject of the next installment.